Hi everyone, this is Abdul Jabber from NI Dresden. Today we are going to show the PriMO-5G mmWave beam management demonstrator. The PriMO-5G project is a project between several partners here in Europe and Korea. The main focus of the project is to demonstrate an end-to-end 5G system providing immersive video surfaces for moving objects. For NI, we have two objectives. The first object is to integrate the G-Node-B and core network, and here we have a collaboration with CommuCore. The second objective is to design a mmWave transceiver and demonstrate mmWave beam management prototyping for 5G in R. And this is what we are going to focus in this demo. As you can see in this figure below, we have the UE on the ground and we have a stationary access drone which emulates the G-Node-B. On downlink, the G-Node-B is transmitting data, while on uplink, the UE is responsible to report the measurements that are required for beam management and control commands, let's say from the incident commander on the ground to the G-Node-B. Our 5G in R research stack implementation is shown on this slide. The block diagram shows the stack starting from RF up to max stop only, since we are focusing on beam level mobility-based beam management. The 5G in R 5-layer implementation is standard compliant. The max stop is used as an API-based entry point for beam management prototyping. The G-Node-B is occupied with 8x8 antenna array, while the UE is occupied with 2x8 antenna array. The mmWave system architecture with related antenna array control, which is integrated to 5G in our research stack, is presented on the next slide. This slide shows the proposed mmWave system architecture based on existing NI SDR. The first component on the right side is the mmWave front-end extension. The IF transmitter receiver represented by NI USRP is connected to up and down converter to shift the IF signal into the frequency range. In our design, the RF 5G mixer is a 24 to 28 GHz up and down converter. In our prototyping setup, an 8x8 and 2x8 active antenna arrays are used on G-Node-B and UE respectively. The second component is the NI USRP, where we have the IF and part of digital baseband signal processing implemented in the FPGA. The last component on the left side is an application, which can be a real-time 5G in R protocol stack consisting of PHY, MAC, and further high-layer functionality, or an unreal-time streaming application that's running on a host PC. Regarding to the antenna array control, it has three components. The first component is initialization. It sets the static configuration that are related to the active antenna array hardware operation. The lookup table represented by beam indices of the selected active antenna array is generated and stored in a DRAM on the USRP FPGA. The second component is the host-based antenna array control. This block is used for beam update, which is part of the beam scheduler. The last component is FPGA-based antenna array control, where we have the whole real-time RF control implemented. This slide shows the components of PriMO-5G mmWave beam management demonstrator. The system components are installed on cards to emulate the PriMO-5G demo concept. They are heavy and we cannot carry them on a drone. In addition, a robot is connected to G-Node B and a game controller is connected to the UE. So we can use the game controller to control the robot remotely via a mmWave link. This emulates the control commands between the incident commandant on the ground and the stationary access drone. In the middle, you can see the host machines. They are used for system configuration, visualization, antenna array control, monitoring, beam visualization for both sides of G-Node B and UE, and the link statistics on both sides. In this demo of millimeter wave beam management for 5G NR, we are going to demonstrate 4 scenarios. The first scenario is downlink data transmission with the high throughput and there is no movement. The second scenario is downlink data transmission with UE movement. And the third scenario is millimeter wave link affected by human body. The fourth scenario is to show uplink user data transmission represented by robot control where the G-Node B is in a movement state and show that the link is stable during the movement of G-Node B.